Life on Earth is full of cyclical variations. We have day and night, the changing of the seasons, and the ebb and flow of the tides. Many of these changes happen over relatively short periods and can be predicted with precision. But other cycles affect our planet over large intervals and can be trickier to forecast. In a previous video, I discussed the role Milankovitch cycles play in the occurrence of ice ages interrupted by warming intervals. But given the vast timeline, it's unlikely our own lives will be very affected by them. Yet, there is one climate cycle that definitely will affect you: the El Nino Southern Oscillation, better known as El Nino and La Nina. While El Nino and La Nina originate in the Pacific Ocean, their impacts are felt nearly everywhere on Earth, and by some accounts, the strongest effects are getting more common. In the last few decades, some of the destructive consequences have included flooding, drought, famine, and mass die-offs of marine life. Indeed, a severe El Nino in 1998 caused an estimated 16% of the world's coral reefs to die, kicking off a cataclysmic mass bleaching event that persists to this day. The ENSO is global and will, without a doubt, impact you. So what are El Nino and La Nina? Why are they linked? And what are their global impacts? I'm Alex McColgan and you're watching Astrum. Join me today as we look at a fascinating climate cycle that became the stuff of legend centuries before we had the science to explain it. If you think the name El Nino sounds more like a folk story than a scientific phenomenon, you're onto something. During the 17th century, fishermen noticed periods of warmer water and poor fishing that would peak around Christmas time. They called it El Niño de la Navidad, which means the boy of the nativity or the Christmas child. It wasn't until the late 19th and early 20th centuries that scientists began to connect a variety of seemingly disconnected regional events scattered across the planet. By the mid-20th century, they found that these weren't regional occurrences, but phases of a global, cyclical phenomenon called the El Nino Southern Oscillation. The ENSO fluctuates with an average interval of 5 years, although the cycle can take anywhere between 2 and 7 years. We've now been tracking these cycles for decades, but they've been around for much longer than that. To understand why the El Nino Southern Oscillation occurs, let's first look at what happens in the Pacific Ocean under normal conditions. Winds blow along the equator from east to west. This is a product of the Coriolis effect caused by the Earth's rotation. Here's a fun fact: if the Earth didn't rotate, air would circulate north to south, from the high pressure poles to the warmer, low pressure region at the equator. As it happens, air does circulate off the poles, but it bends as it approaches the equator. In a circumferential band that extends 30 degrees north and south of the equator, sometimes known as the horse latitudes, air in the northern hemisphere deflects to the southwest, and air in the southern hemisphere deflects to the northwest. This channel of westward moving air is called the trade winds. It turns out they're not just important if you're a pirate living in the 18th century. As the trade winds blow westerly across the Pacific Ocean, they drag warm water from coastal South America toward Asia. And as this warm water moves west, colder water rises to replace it, a phenomenon called upwelling. This cold water is rich in nutrients that feed phytoplankton, which in turn support ecosystems of fish and everything that feeds off them. So, as you can imagine, a shock to this system would have a major domino effect on marine life. If this is what normal conditions look like in the Pacific Ocean, think of El Nino as a disruption of normal. During El Nino, the trade winds weaken. As they slow down, warm water that would be flowing toward Asia builds up instead near the coastal Americas, resulting in less upwelling cold water. This, in turn, creates a zone of warm air and water further east in the Pacific. With less upwelling, the fish that feed off the phytoplankton migrate or die. The Pacific jet stream that crosses North America moves south from where it normally occurs. As a result, the northern United States and Canada tend to become warmer and drier, whereas the Gulf Coast and parts of the coastal South America become wetter. Peru and Ecuador receive their wettest months from April to October, and during more severe El Nino years, rain and flooding in those regions can be catastrophic. In the severe El Nino of 1997 to 1998, devastating floods bombarded Peru, collapsing bridges and burying entire shantytowns under a meter-thick layer of mud. In total, 250,000 people were displaced from their homes. The region of Tumbes, which is normally arid, received an unbelievable 16 times its average annual rainfall. Outside the Americas, El Nino sets off a series of domino effects that significantly alters weather worldwide. The increased rainfall in South America typically coincides with a pronounced period of drought in South Asia and Australia. Severe famines have been recorded in India, and a delay in Australia's monsoon season can lead to massively destructive bushfires. Due to its vast expanses of grassland, Australia's bushfires are some of the most destructive on Earth, and there are already concerns about an event that could occur late in 2023. Leaders are understandably worried given recent warming trends. You may remember that in 2020, in a non-El Nino year, bushfires wrought nightmarishly apocalyptic scenes that left 50 million acres of land charred to a crisp. Australia is a literal tinderbox over which El Nino looms like a proverbial flamethrower, so local officials are wise to prepare for the worst. On a global scale, the average surface temperature during El Nino rises 0.1 degrees Celsius. But not all El Nino events are severe. Some can be rather mild, something to keep in mind before you hit the panic button. The average El Nino lasts from 9 to 12 months, but on rare occasions they have lasted for years. The world's climate is a pretty complex system responding to a number of inputs, so the effects of El Nino are best understood as relative to what the baseline would be, which is why no two El Nino years are alike. La Nina is the opposite side of the El Nino Southern Oscillation. If El Nino is a hot event, then La Nina is a cool one, although some regions do experience warming. As I mentioned earlier, El Nino occurs when the equatorial trade winds slacken, but during La Nina, the trade winds become even stronger. Think of El Nino as a disruption of normal and La Nina as normal plus. The trade winds blow even more warm water from coastal South America toward Asia, resulting in more upwelling of cold, nutrient-rich water near the Americas. For fisheries, this can produce a feeding frenzy. And if you like salmon, well, you're in luck. During La Nina, cold water species like salmon will venture into typically warmer waters where they can't ordinarily survive. The same is also true of squid, in case you prefer calamari. Meanwhile, in Asia, the influx of warm equatorial water produces wet conditions, the opposite of the drought experienced during El Nino, causing a spike in tropical cyclones. In North America, the jet stream is pushed further north. This causes drought in the southwestern United States and rains in the Pacific Northwest. In 2022, La Nina exacerbated a mega drought in the southwest United States, making it the worst in 1,200 years. Just look at this image of Lake Mead, where the Hoover Dam is located. That light area is the so-called bathtub ring, ordinarily covered by water. Now, with all this talk of trade winds and jet streams, you might be wondering how La Nina affects hurricane season. Well, depending on where you live, the news is either good or bad. The Atlantic often experiences a much more severe hurricane season during La Nina because the shift in the jet stream produces greater atmospheric instability in the southern Atlantic. But the Pacific Basin actually sees fewer hurricanes, a sign of how drastically different these regional effects can be. Just don't get too complacent, Pacific dwellers. El Nino has the opposite effect as La Nina. Meanwhile, in Pacific coastal South America, you won't see the warm Christmas-time waters that once prompted fishermen to dub it El Niño de la Navidad. Indeed, there's a reason why fishermen once called La Niña El Viejo, or the Old Man. During La Niña, the weather in Peru and Chile turns colder and drier, sometimes producing severe periods of drought. Brazil's north, on the other hand, becomes wetter during the months from December to February, and the lowlands of Bolivia can receive catastrophic flooding. In Africa, the conditions in La Niña years are basically the reverse of what they are during El Niño. East Africa tends to experience drier than average conditions, whereas the south tends to be wetter than average. So, where are we now in the ENSO cycle? As of the making of this video, the National Oceanic and Atmospheric Administration has declared an end to a lengthy 1.5-year La Niña. They concluded this based on measuring the difference in surface atmospheric pressure in the western and eastern Pacific, a metric known as the Equatorial Southern Oscillation Index. The last reading of it was just 0.1, down from 1 a year ago, meaning conditions have returned pretty much to normal. It's still early to say anything definitive, but there are already indications that an El Niño will occur later in 2023. Currently, the NOAA is forecasting a 60% chance that El Niño sets in by autumn. This would have major ramifications, and India is already warning its citizens of potential drought conditions. There's another reason to expect an El Niño in 2023, albeit based purely on past experience. Since we started tracking in the 1950s, there has never been more than a 4-year period without an El Niño event. So if there isn't one in 2023, it would mark the first 5-year gap without one. For me, this is an excellent example of how studying climate cycles can help us prepare and foster human survival, not just on this world, but potentially on other worlds too. Because one of the fascinating aspects of the ENSO is the level of insight we gain from it into Earth's complex climate systems. Understanding the interconnectivity of our own planet's climate will be crucial if we ever want to settle on other planets or even terraform. If humans eventually undertake the huge task of terraforming Mars, Mercury, Venus, or the Moon, or perhaps even an exoplanet in some other part of the Milky Way galaxy, our success will likely depend on our ability to understand the various inputs and feedback loops that intricately interlink climate systems and biospheres. That day may seem far off, but it isn't too early to start dreaming. So, there we have it, an in-depth primer on the El Niño Southern Oscillation. The ENSO can be a very destructive cycle for our planet's animal and human populations, but life is nothing if not adaptable. Likelier than not, 2023 will add another piece to the growing body of documentation about these events. How has El Niño or La Niña affected you? Have you noticed any interesting changes in your part of the world? I'd love to hear about it in the comments. "Winter is coming," said Eddard Stark. When he uttered his famous words in the TV series of Game of Thrones, it was more than just a pronouncement of the normal passing of the seasons. Rather than lasting a mere 4 months, winter in the fantasy realm of Westeros could be a big problem. It could potentially last for years, even up to a decade. Crops would be harder to grow, the weather would be colder. The arrival of winter was the harbinger of an era of hardship. Of course, while Westeros is pure fantasy, seasons that last for years on end are not limited to fictional stories. We experience them on Earth. Various cycles are playing out on our planet, and when they are in conflict, we experience a period of stability. It's worth noting though that they will not be in conflict forever. In our future, winter is coming too. But what are these cycles? How can better understanding them help us prepare for our future? I'm Alex McColgan and you're watching Astrum. Join me today in exploring the different cycles that affect our planet's weather and warmth. To begin, we should probably ask a simple question. what causes the seasons that we are familiar with? You may well already know the answer to this question, but as it will provide the starting point for what comes later, it's worth reviewing. Besides, this question is not entirely straightforward. Depending on where you are on the planet, you may not actually get any seasons. Generally speaking, seasons we know of are caused as a result of our planet's tilt. Because our planet rotates at a tilted angle as it orbits the Sun, one hemisphere will point towards the Sun during part of the year, while the other will point away. Naturally, hemispheres that are pointed towards the Sun become much warmer, while pointing away from the Sun makes them colder, creating the regular seasons, summer and winter. This effect becomes stronger the higher up or lower down the planet you go. Consider the small Norwegian town of Tromsø. Because of its higher altitude, Tromsø isn't just pointed more towards the Sun. The tilt of the Earth is such that from its perspective, the Sun never sets for months in summer and never rises for a few months in winter. Naturally, this produces quite the seasonal variance. But this effect lessens the closer to the equator you get. There, the tilt of the Earth doesn't really change how close or far away from the Sun the area is, and as such, the Earth doesn't notice much temperature variation. It's all just a question of how close you are to the Sun. However, did you know that the tilt of the Earth isn't static? Nor is it the only thing about a planet's orbit that influences how warm or cold we are. Imagine for a second the model you are familiar with, of the Earth orbiting the Sun in a nice circle, flat to the plane of the solar system. In this model, we circle the Sun because of the Sun's gravity. This model is too basic. In reality, the Sun is not the only source of gravity pulling at us, although it is the biggest. Many of the planets pull and tug at us, particularly large ones like Jupiter, which has a mass 318 times the size of our own planet, or Saturn, which is 95 times. And we, in turn, pull on them. As planets all rotate at different speeds around the Sun, this constant pulling and releasing creates a delicate dance, far more complicated than a simple circle. This interplay of increasing and lessening gravity has many different effects on our angle of tilt, our orbit, and even the plane in which they occur. Broadly speaking, these variables have stabilized into cycles. These cycles were first described effectively by Serbian geophysicist and astronomer Milutin Milankovitch in 1920, and thus were called Milankovitch cycles. The first such cycle I want to look at is the changing shape of our orbit. Over the course of a 100,000 year period, the Earth's orbit around the Sun becomes more and then less elliptical. Naturally, if our orbit is closer to that of a circle, our distance from the Sun remains relatively consistent, and we get about the same amount of sunlight all year round. However, once our orbit becomes elliptical, there are parts of the year where we are further from the Sun and thus colder, and parts where we're closer and warmer. As it happens, the perihelion of the Earth's orbit, or the bit where we're closest to the Sun, happens roughly on January 3rd, while the aphelion, or the bit where we're furthest away, happens on roughly July 4th. I'm recording this in the UK, which means for my hemisphere, January is winter. So for me, this is quite nice. Although we are in a phase right now where this cycle of the Earth's orbit is more circular than it is elliptical, we still experience a 7% difference in the amount of sunlight we receive in January compared to July. This sunlight difference means that my northern hemisphere's winters are warmer, while our summers are milder. In the southern hemisphere, the reverse is true. Because they're experiencing summer during this warmer phase, their summers become even warmer, winters become colder. And that's just at this stage of the 100,000 year Milankovitch cycle. As the Earth's orbit becomes more elliptical, that 7% sunlight difference turns into a 23% difference. Quite significant. You might think this seems overall a little unfair on the southern hemisphere. The northern hemisphere benefits from this cycle stabilizing its seasons, while this cycle makes the southern hemisphere's seasons more extreme. Don't worry though, as another cycle is at play to bring things full circle. This current seasonal rotation happens because the Earth's tilt is consistent as it orbits. Except it isn't consistent. Little by little, the angle the Earth's axis is rotating along is changing too. It moves as if it were drawing a circle on the sky above it, in a cycle that lasts 26,000 years. One upshot of this is that while our axis is currently pointing at the North Star, or Polaris, this will eventually no longer be the case. Over time, it will point at different stars, before eventually circling back to point at Polaris again. The other upshot of this is that in 13,000 years, the Northern Hemisphere will be having its summer in January, while the Southern Hemisphere will be the one with a white Christmas. So, then it will be us experiencing a more profound seasonal variation. While harsher winters are unpleasant, they are not what I promised. I started this video by describing seasons that lasted years. These exist too. There are Milankovitch cycles that create winters that last for thousands of years. Or, to speak more accurately, there are Milankovitch cycles that help cause ice ages. We don't fully understand how ice ages come and go. There are numerous theories. However, it must be noted that some of the 100,000-year spans of ice ages line up extremely well with the 100,000-year Milankovitch cycles. For instance, there is a cycle whereby the plane on which the Earth rotates around the Sun rises and falls over the course of 100,000 years. This change in its orbital inclination does not obviously explain why it is that the Earth would be getting colder or warmer. After all, the Earth is still the same distance from the Sun. However, it lines up so perfectly with the time periods ice ages were occurring at over the last 800,000 years that scientists conclude that there must be a connection. Perhaps cosmic dust lying in the plane of Earth's orbit blocks out some sunlight when we are at one inclination, but is not in the way when we are at another. This could go some way toward explaining the occurrence of ice ages during these time periods. Whatever the case, there is at least one other cycle that influences the arrival of ice ages on Earth, and this might perhaps be the most important for us today. It is the tilt of Earth's rotation. I already mentioned that this axis of tilt rotates around the planet, but it also changes the angle at which it does this. Over the course of 41,000 years, it alternates between 21.1 degrees and 24.5 degrees. At the moment, it is 23.4 degrees and is declining. You might think that this is a good thing. The smaller the angle of tilt, the less extreme our seasonal temperature variations might be, and the warmer our winters will become. Surely that is a good thing for avoiding ice ages. Surprisingly, it is quite the opposite. Left to its own devices, this lessening tilt would lead us into another spreading of the ice sheets and cooling of the planet that would hit its peak in 9,800 years. It is not the harshness of the winter that causes this spread, but strangely enough, it is the mildness of the summers. You see, when winters occur, snow builds up at the top of mountains and in cold polar regions. In warm summers, this snow tends to melt away. However, if the summer is mild enough, the snow sticks around, becoming a more permanent feature of the landscape. Icy snow is white in color and reflective, which means that light has a tendency to bounce off it rather than be absorbed by it. This means that if the Earth is covered with ice, it reflects sunlight back into space and actively becomes even colder, thus creating conditions for even more ice. In more than one sense of the word, this is a snowball effect. We are right now in an interglacial period. This is a brief moment of warmth that lasts a few tens of thousands of years or so, interspersing a deeper, more general cold trend. If it wasn't for this warmer uptick, we would actually be in an ice age right now, and from a technical perspective, actually are in an ice age, just one we're not fully noticing. If it wasn't for this briefly warm interglacial period, mankind would have experienced ice across the history of its entire existence. Thanks to the Milankovitch cycles, that brief period of warmth will someday end, then winter will truly come. Of course, this is under the assumption that Milankovitch cycles are the only factors that influence global temperatures. And while broad trends lasting 100,000 years and interspersing upticks every 41,000 years are indeed demonstrable and consistent in parts of fossil record, the location and orientation of our planet are not the only thing that matters. CO2 and methane levels in the atmosphere are also driving forces behind global temperature fluctuations. And if we're not careful, just as an ice age can build up with a snowball effect, stripping away of ice can happen in the same way, but in reverse. Less ice means less reflection of sunlight, making things overall warmer, which leads to less ice. Still, if Milankovitch cycles are the only factor in action, we are in for a cold future. The Milankovitch cycles affecting the planet currently are mostly working to stabilize the system, leaving us in a temperate, relatively even temperature zone. However, there will come a time when they will make temperatures, hot and cold, more extreme. We would do well to keep these cycles in mind. Milankovitch cycles are in it for the long haul. Winter might not be coming for a long time, but one day our planet will face winter again. It's getting hot outside. Nowadays, it's difficult to turn on the news without hearing someone talking about global warming. Headlines are filled with references to rising temperature levels, fossil fuels, and encroaching danger. And the discussion around the subject has gotten as heated as the weather. This has been a topic I've been wary about weighing in on, simply because of how sensitive a subject it has become in recent times. I've sat on this particular video for 3 years, occasionally updating it, but not quite feeling it was the right time to release it. I didn't want to simply create more noise. However, I do now think there is something worth adding to the discussion. After all, there is plenty we hear about the current temperature of the planet. What is often not talked about is the patterns of temperature change that existed in the past that contextualize that modern temperature. Are we really the hottest we've ever been? Scientists believe that in the last 100 years, the global temperature has been increasing. But how does this fit into wider patterns and trends? And how did they find any of this out? I'm Alex McColgan, and you're watching Astrum. And today, we will be taking a closer look at the data recording the temperature history of our own planet. It's only by understanding the ancient past that we can contextualize the current discussion on global warming and answer, what exactly are scientists so worried about? So, to begin, how do we know what the temperature used to be? It's easy to find the current global temperature today. All you need is a thermometer, and you can go outside and take a reading. With enough readings taken at different locations around the globe, you can find an average temperature for the whole planet. Scientists have actually been doing this since 1850, meaning that our records on average global temperatures are fairly accurate since this date. However, mercury thermometers were only invented in 1714. So how do we know what the temperature was before these global readings started being taken? How do we know the temperature 1,000 years ago, or even 1,000,000 years ago, before humans were on the scene? Some of you may already know the answer, or at least a partial answer. Scientists can approximate global temperatures in the past through ice coring. Essentially, when snow falls, because it is powdery, it traps little bubbles of air where it lands. If this snow doesn't melt, but has more snowfall on it later, such as in a very cold place like a glacier, you can end up with layers of snow and ice trapped air bubbles going back for many, many years. It creates something similar to the rings on a tree. By collecting ice formed this way, scientists can take sections to a lab and melt it, releasing the air relating to specific years. They then can measure the different ratios of gases released from the air bubbles, which tells them the atmospheric composition at that time. And because we can test how much heat is retained by a gas when exposed to a constant temperature like the sun, for instance CO2 retains more heat while oxygen retains less, with enough samples, scientists can calculate roughly what the global temperature was during that year. However, the oldest glaciers are only 1,000,000 or so years old. To get a good idea of the trends that govern global temperatures, we're going to have to go back much earlier than that. How do we know what the global temperature was over 1 million years ago? The answer might surprise you. Clams. Actually, not clams, but something similar. A tiny single cellular organism no larger than a full stop called foraminifera. Like clams, these organisms produce shells around themselves, and these shells are slightly porous. Oxygen in particular is taken into the shell and trapped there, remaining in place even when the foraminifera dies. So, using a similar process to the ice cores, if scientists can find shells of dead foraminifera from a particular year, they can release that air and work out from it the global temperature. This process is slightly different, as instead of air composition, scientists are looking at different oxygen isotopes, but basically it's a very similar process. Foraminifera are still around today, and first came onto the scene 500 million years ago, so they are instrumental in helping us get a clear picture of global temperatures during this much longer time period. But what is that picture? Based on data collected from foraminifera, it looks something like this. There is a certain degree of uncertainty to this. Findings get more reliable the closer we get to the present day. But as you can see from general trends, the Earth's temperature has undergone significant changes over the last 500 million years. At times it has faced temperature averages 14 degrees Celsius hotter than we have today, and at other times about -5 degrees Celsius lower. So we are not the hottest we have ever been. Then again, that's not surprising to anyone who knew that the surface of the Earth when it was just formed was mostly magma. But you may not have expected these fluctuations. Why are they happening? Scientists are not entirely sure, as there doesn't seem to be much of a pattern to them on this grand scale, but they believe that some of these fluctuations are from the emergence of new life forms. For instance, the arrival of plants at around 450 million years before the present might explain why the temperature dropped then. They started absorbing atmospheric CO2 and turned it into oxygen, which retains less heat. Other changes could have been caused by plate tectonics and volcanic activity putting more CO2 into the air, and still other changes could have been caused by possible meteor impacts, like the one that wiped out the dinosaurs. However, this is not the full picture. By increasing the resolution and zooming in slightly, we begin to see another interesting trend. Let's look at the 65 million year picture. Within the large sweeping changes, it turns out that there are many smaller fluctuations. These become more obvious when we zoom in again. And again. And again. By this point, we can see a distinct, smaller pattern occurring. Rapid rises in global temperatures, followed by gradual dips. It's hard to get your head around the sheer scope of the Earth's history, but each one of these dips represents entire ice ages. Ice ages are technically defined as any point in Earth's history where there is ice on the polar caps, something that is not always the case. So technically, as I've mentioned in a previous video, we are in an ice age right now. However, although the general trend of the Earth's temperature at the moment is towards ice ages, we are in something known as an interglacial period, a span of many thousands of years where the Earth is temporarily warmer in between full ice ages. In the last full ice age, the polar caps reached the UK and parts of the US. But what is causing these dips and rises on our graph? Well, I go into more detail about this in my video on Milankovitch cycles, which you can watch here, but just to brush up on them very quickly, Milankovitch cycles are the periodic changes that take place within our planet's climate due to fluctuations in its orbital movement around the Sun, usually over the course of thousands of years. Surface ice affects the temperature of a planet. The more surface ice a planet has, the colder the planet tends to be, as more heat is reflected back into space. But equally important is the direction that surface ice is facing. Consider ice to be like a shield that will reflect the sun's rays. If that ice is not pointed in the direction of the sunlight, it cannot reflect it. So anytime the planet points its surface ice towards the sun, the Earth tends to get cooler, creating something of a feedback loop. This matters because the Earth's axis isn't stable. Over the span of thousands of years, it moves back and forth, sometimes pointing the polar ice caps more towards the sun, and sometimes pulling them further away. Although this change is only a couple of degrees at most, it is enough that over time it has an impact on the global temperature. The temperature drops as the ice shield faces the sun and rises again as it points away. This fluctuation is one example of a Milankovitch cycle. There are other Milankovitch cycles, which are consistent cycles in the Earth's orbit that affect its temperature, acting on timescales of 23,000, 41,000, 100,000, 405,000, and 2.4 million years. Whenever these coincide with each other, they create even greater changes to the global temperature. You can see the gaps between the ice ages in this graph tend to be about 100,000 years apart, perfectly in line with one of the Milankovitch cycles, specifically the change in the Earth's orbital eccentricity. But all of the cycles have an impact. So where are we in relation to one of these Milankovitch cycles? Let's zoom in some more. As you can see, we have risen out of an ice age and have entered a fairly stable plateau of global temperature. This is consistent with the rapid rise in temperature / slow drop in temperature that characterizes ice ages and the periods between them. All of human history, from the pyramids to the present day, can be found on this plateau. Although humans existed before this point, they hadn't really got the hang of building any civilizations. Scientists have named this plateau where human history began the Holocene period. However, the uptick right at the end is not so usual. This uptick represents a rise in the global temperature by 1 degree, which technically is still roughly on par with the interglacial period before our current one over 100,000 years ago. However, it is not the temperature change that is concerning about this uptick. It is how quickly it is rising. Unlike all the other changes on all these graphs, which have taken place over hundreds of millions of years at the longest and thousands of years at the shortest, this rise took place in 100 years. This could have a big impact on the ecosystems on the planet. So, what could have caused this uptick? The answer cannot be Milankovitch cycles. As you have seen, these cycles take place on the scale of thousands of years at least, and millions at most. Even when we zoom in on sections of our graph where there appear to be sharp upticks, we realize that these rises take place over a couple of 1,000-year periods. Milankovitch cycles are described as weak but consistent forces, like the trickle of a stream that eventually erodes a mountain. They do not create effects over such a small time frame as 100 years. Similarly, there has been no cataclysmic event such as the one that wiped out the dinosaurs, which might be our other explanation. That meteor was thought to be 10 kilometers wide and struck with a force of 21 to 921 billion Hiroshima A-bombs. About 75% of species died in the climate change that happened in its aftermath. If something like that had hit Earth since 1850, we would have noticed it. However, there is one factor that does explain this change in global temperatures: the activity of humans. It is not the first time that living organisms have had an impact on the global temperature. Remember, it is believed that some of the changes we see here are caused by the introduction of plant life absorbing CO2 and releasing oxygen. Similarly, back when life was still all single-celled organisms about 2.4 billion years ago, the arrival for the first time of cyanobacteria that could photosynthesize had a massive impact on the atmosphere. For the first time, an organism started putting oxygen into the atmosphere. This occurred at such a rate there was an event known as the Great Oxidation Event, which coincided with a significant drop in the global temperature. Some scientists believe the entire world almost froze entirely over, as there is evidence of glacial activity at the equator, a snowball Earth as it came to be known. What we learn from this is that the balance of global temperatures is very delicate. A single species that starts to change the atmospheric ratio of gases can have a massive impact, overloading the subtler effects of Milankovitch cycles. And since 1850, humans have definitely changed the way we have been interacting with the atmosphere. Unlike the previous roughly 10,000 years of human history, since 1760 and the Industrial Revolution, human activity has produced vast amounts of greenhouse gases as a waste product of industrialization and farming. In the last 4 decades, each decade has been the hottest decade on record since we started tracking global temperatures in 1850. CO2 levels are now at a global average of 410 parts per million, and methane at 1,866 parts per billion, which is higher than we have seen in the last 800,000 years, which means since before about 8 ice ages and interglacial periods between them. And importantly, the global cover of surface ice has been retreating consistently since 1950, something scientists do not believe to have happened for the last 2,000 years. As you will recall, this has a knock-on effect on Milankovitch cycles, as a planet with less surface ice does not reflect as much heat from the sun, so tends to get even hotter. Like pushing a cart down a hill, these changes have a certain amount of momentum to them. And sadly, rapid changes in global temperature tends to lead to species going extinct. It normally takes thousands of years for life to adapt to the conditions you might find during an ice age, woolly mammoths, to conditions today, elephants. Natural selection takes time to develop in a species the traits they need to thrive in a new environment. If species are not given this time, they either have to move to a new environment better suited to them, or they will die out. As the habitable zones begin to migrate towards the poles, some zones will vanish completely, while new, hot desert environments will be created that life in general is poorly adapted to. It's important to note that these events are not unstoppable. Global temperature change does have some momentum, but if we as humans find ways to stop changing the atmosphere's ratio, then in time, Milankovitch cycles will take over again and the rise will stop. That's why it's so important for governments to listen to reports by institutions like the IPCC, an international group of scientists funded by multiple governments tasked with finding out the realities of climate change, who in 2021 released their 6th assessment report explaining the physical science basis. In it, they stated that it is unequivocal that human influence has warmed the atmosphere, ocean, and land. However, they also offered suggestions, namely the importance of halting or rapidly reducing CO2 emissions towards net zero, as CO2 is the largest contributor towards climate change, followed by methane. They also recommended the development of carbon dioxide removal facilities to be established worldwide. Some of these are already in operation, such as Project Longship in Norway. Their aim is to take CO2 out of the atmosphere and bury it beneath the ground in depleted fossil fuel reservoirs. The IPCC says that actions like this, if widespread enough, will reduce global surface temperature and even reverse certain other processes like acidification of the oceans. Personally, I'm not super convinced by current carbon capture projects, but they do exist. But these efforts need to be done on a large-scale government level. Ultimately, my aim for this video was to examine what global warming meant within the context of Earth's wider history. From it, we can see that it's not actually accurate to say that we're the hottest we've ever been. And I find that a really fascinating insight. However, that fact alone is not the reason some people think it is to not worry about the problem. Climate change is a process that usually takes millennia. I've realized the worrying part is not necessarily the change itself, but rather the speed at which it is happening. Some life forms might get left behind. And how will humanity cope? We don't know, as we haven't been around long enough to deal with the extremes of the past. While human activity has sped up certain elements, and while we can undo some of what has been done through our actions now, some things, like higher sea levels, will be with us for up to 1,000 years. According to the latest IPCC report, we are past the point of no return for 1.5 degrees Celsius, and will need to make rapid, fundamental changes to our society this decade to stop it going any further than that. This will be hard. There's no way we as a species will be able to achieve this hard path unless we can agree on the facts that underpin it though. Without the broader context of agreed upon data, it will forever be perfectly possible to arrive at a wide range of conclusions and different paths we should take. That is why, when it comes to any discussion, context is so important. By looking at the pattern of our planet's history, we see that the current uptick in global temperatures is an induced event that doesn't match already existing patterns, and it perfectly coincides with human activity. Debate what you want to do with that information and the best path to take in light of it, but these are the facts, set in ice and the bones of organisms long dead. They will brook no argument. When I started my Milankovitch cycles video with a reference to Game of Thrones, I didn't realize exactly how apt my analogy was. In that TV show, the armies of the Night King in the north are trapped behind a giant wall. Just like in the TV show, it turns out that on Earth there exists a powerful, icy force to the north that is seeking to overthrow its bounds and rush southward. That powerful winter is also kept at bay by a mighty wall, one that allows the nations to the south to enjoy relatively tranquil conditions. And just like in the TV show, that wall eventually gets breached in a wave of ice that sweeps down and threatens the lives of all those in its way. You might not recognize what I'm talking about. Where is this wall? And what is the icy winter it protects us from? The answer to the first question is a name that I find particularly cool: the polar night jet. And it turns out that the polar vortex it protects us from is a biting chill not to be underestimated. What is the polar vortex, and how does the polar night jet protect us from it? I'm Alex McColgan and you're watching Astrum, and today we'll learn more about this climate-shattering phenomenon and what happens whenever the polar night jet breaks down and the polar vortex is unleashed. There are actually two polar vortexes, one at each pole of the planet. And even there, each vortex comes in two parts: a tropospheric polar vortex, spinning in the section of the atmosphere known as the troposphere, from ground level up to about 10 to 15 kilometers. This is where 75% of the total mass of the atmosphere resides. Above that lies the stratospheric polar vortex, a technically separate weather phenomenon that has its own size, seasonal cycle, and influence on the global climate. Each of these massive cyclones sits over the pole, spinning with the planet's rotation, with wind speeds that can reach up to 240 kilometers per hour. Why do these winds happen? The first piece of the puzzle is temperature difference. At locations like the equator, where sunlight is most concentrated, the air is warmed and starts to rise. As it does so, it creates an area of low pressure beneath it that draws air into it from its surroundings, like a giant vacuum cleaner. Meanwhile, at places like the poles, where it's much colder, air contracts and falls, creating zones of high pressure, where air molecules want to spread out like a crowd of school children being released into an open field. So, naturally, with these two forces at play, there is a tendency for air to rush from the poles towards the equator. Freezing cold winds are constantly trying to escape from the north and south poles. This model is a little simplified though, as wind does not travel in one continuous line from the pole to the equator. Instead, because air from the equator cools and falls much sooner than the pole at around latitude 30 degrees, and air from the poles warms and rises much sooner than the equator at latitude 60 degrees, there are 3 cells of air on each hemisphere that air circulates in. The polar cells, the air masses above the poles, and the Hadley cells, the air masses above the equator, both cycle in the temperature-driven way I described. However, the middle cell, known as the ferrule cell, is not temperature-driven. Like a gear, it is dragged by the rotation of the other 2 cells and rotates opposite to their motion. In terms of our northern polar vortex, this means that once the air from the pole heads south, it's met by warmer wind traveling in the opposite direction. And when 2 air fronts of different temperatures meet, they clash rather than mix. So the polar vortex is trapped, bounded, clashing against winds coming in from all sides. There's more at play here though. If this was on its own, the cold air from the north would just slide underneath the warm air from the south, not really being trapped at all. There is a second force at play that redirects those winds, spinning them into a vortex that keeps them circling the poles rather than coming down towards the equator. Where does this spin come from? It's due to something known as the Coriolis force. In a simple, flat world, cold wind from the poles would travel towards the equator, while warm wind from the equator would float over it towards the poles. But the world isn't a simple flat sheet. It's a rotating sphere. You are traveling right now at somewhere between 0 km per hour, if you're at the pole and decided to watch an Astrum video while you're there, and 1,600 km per hour at the equator, from the west to the east. You might not notice this fact because everything next to you is, on average, traveling at the same speed in the same direction. But what happens if you were to travel from the equator to the pole? Conservation of momentum states that you would still be traveling eastward at the same speed as previously, but suddenly the Earth beneath you is not traveling quite so fast. Remember, at the pole you'd have 0 eastward speed, but would simply be rotated slowly. If, on the other hand, you keep all your eastward momentum from the equator and travel towards the pole, suddenly it will appear, compared to everything else, like you are traveling east really fast. In practice, this means that air that travels up towards a pole from the equator, whether towards the North Pole or the South, will not go straight up, but over large distances will start to curve towards the east. This rapidly eastward traveling air is why you get jet streams. There are at least 4 of these, straddling the gaps between the Hadley cells, the ferrule cells, and the polar cells. The subtropical jet stream lies between the first 2 and is a little weaker, but the jet streams we are interested in are the polar jet streams, wringing the frigid air off that develops in the north and south poles. These ribbons of air circle the globe in an almost continuous path, a little underneath the boundary between the troposphere and the stratosphere. They are only a few kilometers deep, but can be hundreds of kilometers wide, and in their hearts, the wind can travel at 400 kilometers per hour. As a reminder, over 120 kilometers per hour is getting into strength level of hurricanes. The jet stream around the South Pole is fairly stable. Its powerful winds overrule the polar winds trying to leave the polar air mass, whipping them along with it and dragging the entire polar cell into a massive Antarctica-spanning vortex. At this point, a keen-eyed observer might have noticed a flaw in this model. If conservation of momentum means that air going from the equator towards the pole veers towards the east, why is it that air traveling from the pole towards the equator doesn't do the exact opposite? It has 0 momentum, moving to zones that have considerably more momentum. Comparatively, it should be quickly left behind, appearing to start spinning to the west. This is true, but cold winds have much more friction to contend with as it starts to slide underneath the warm front and then drags along the ground. This seems to slow it down enough that the countervailing jet stream overrules it. It's important to note this tension at play though, as it becomes much more important in the polar night jet. The polar night jet is the jet stream that bounds the vortex at the North Pole. Specifically, it bounds the stratospheric polar vortex, keeping it in check during the coldest part of the year for the North, the polar night. Here, during the winter months, the sun is absent from the sky entirely, creating even more freezing temperatures. Interestingly, this colder climate creates a deeper pressure difference between the air around the pole and the air further south, which actually strengthens the force that creates the polar night jet, meaning that during the coldest part of the year, this freezing air is usually well contained. However, this does not always hold true. There are things that can disrupt a jet stream. There are certain zones, such as the boundary between sea and land, or the presence of a large mountain, that can cause disruption to wind. Coastal environments create their own winds that can suck in jet streams, while mountains force an air current to move around it. Even other weather phenomena, such as El Nino, which you might recognize from one of my recent videos, can have an impact on the path the jet stream takes. As the jet stream is not fixed down, but is a balancing point between a range of opposing forces, hitting such obstacles causes it to deviate from its course, and once it starts deviating, it will rock back and forth like a string that has begun bouncing. It shifts, no longer in its balance, overcorrects itself, and is no longer in balance again, and overcorrects itself again, in massive planetary waves that cause the polar night jet to meander around the Earth rather than travel in a straight line. And these oscillations can reach a point where there is a breach. The first sign of this comes in the form of a sudden stratospheric warming, most common in late winter. An SSW can even represent a time where temperatures rise in the polar region by as much as 50 degrees Celsius over the course of just a few days. Something within the system of the jet stream can be so thrown by this that it leads to the southern moving westerly winds overpowering the jet stream, partially or completely reversing its flow. No longer contained, Arctic wind moves south and meets warmer and warmer air, and pushes faster and faster south in an attempt to balance the gradient. The entire jet stream buckles, and suddenly it pivots. It massively reorients itself, traveling down the planet so that regions like Europe and America, usually safely on the warm, temperate side of the polar night jet, suddenly find themselves in the domain of the polar vortex. The forces of winter have arrived. In fairness, not all of these events are devastating. With sufficient preparation, you can simply put on some warm clothes or try to avoid going outside for the month or so that the polar winds are overhead. As long as you're ready for cold, it's not the end of the world. However, sometimes the outcome is serious. In the UK, in 2009 to 2010, the Big Freeze saw parts of Scotland reaching temperatures as low as minus 22 degrees Celsius, the coldest in nearly 40 years, with widespread transport disruption, event closures, and power failures. Sadly, this in turn led to the death of 25 people. In the US, the 2019 January-February North American cold wave saw a polar vortex move down across much of the country with similar outcomes. Some areas saw temperatures as low as minus 50 degrees Celsius, if you take into account wind chill factor from the blustery, freezing winds. Snowstorms raged. You could get frostbite from being outside in just 10 minutes. Sadly, another 22 people died, with hundreds more needing frostbite treatment. Responsible was the ranging polar vortex. In time, the imbalances in the global temperatures restore themselves, and the jet stream returns to its previous position. However, it's worth noting that some level of jet stream breakdown occurs in the north 6 times every decade. If you live in the northern hemisphere, you will likely see many more of these events over the course of your lifetime, although hopefully not all as powerful as these 2 examples. In the south, you are likely safer. There have only ever been 2 instances in recorded history of the solar polar jet stream breaking down in the same way as the northern one. It has happened though, and the mechanisms behind it are not fully understood. It's difficult to say, as global temperatures gradually rise, what influence this might have on the jet streams. Some evidence indicates that they are traveling further poleward on average year on year, although this is apparently not unheard of in the planet's history. There is some more evidence that the jet streams have strengthened since 2002. If so, we should be grateful. Although unpleasant, the biting cold of the polar vortex usually is only a passing weather phenomenon. We see it return north within a month, but if the jet stream were to go, the polar vortex would come down from the north to stay, and we'd truly know what it is like to live in Arctic conditions. The more I've learned about this subject, the more I've discovered that the winds of our planet are this fascinating weave of interplaying forces and effects that tug and pull on each other, finding perfect balances and yet constantly shifting in rhythms and patterns. And yet, it does so practically invisibly. So much is going on that we simply do not see down here on the ground, just because air is, well, air. And yet, I've learned its importance. The polar night jet is not just wind with a cool name. It is a bastion of protection, a wall against the frozen wind. It really makes you think of the incredible majesty of the world around us, how much is going on that protects us that we simply do not see. Imagine a force so powerful that it can change weather patterns around the world and even alter the fate of ancient civilizations. Earth's short-term weather patterns and long-term climate are influenced by a complex collection of factors, from our place in the solar system and the planet's rotation to atmospheric patterns and seasonal changes. To further complicate things, every few years our planet experiences El Nino and La Nina events, 2 opposite ends of a scale that are part of the El Nino Southern Oscillation, or ENSO for short. Evidence of the ENSO goes back tens of thousands of years, and may have even played a role in destabilizing some of the world's great ancient civilizations. One of the 5 strongest El Nino events ever recorded has finally come to an end as of June 2024, after months of record-high ocean temperatures, unprecedented heat stress on coral reefs, drought in the Amazon rainforest, and extreme rainfall with dangerous consequences for North America. With La Nina predicted to begin late 2024 or early 2025, what changes can we expect globally and locally? I'm Alex McColgan, and you're watching Astrum. Join me as we take a look at our changing planet, the ENSO, and what La Nina will do to Earth. Our previous video about El Nino explored one side of a global cycle that typically takes between 2 to 7 years to swing from one extreme to the other. These El Nino and La Nina episodes usually last 9 to 12 months, but can last several years. In this video, we will take a closer look at how this cycle works, what neutral periods are, and what might happen as we head into the opposite extreme of La Nina in the coming months. When our Earth experiences average conditions, we call those periods ENSO neutral. But every few years, fluctuations in wind and ocean surface temperatures can signal the beginning of an El Nino or La Nina event and a departure from Earth's normal conditions. These events alter worldwide atmospheric patterns and are known to wreak havoc by contributing to extreme weather and environmental harm. Imagine we're on the International Space Station orbiting Earth. From here, we can see our planet's spherical shape, and as you might expect, sunlight affects the Earth's surface unevenly. More light and heat reaches the Earth at the equator, where sunlight strikes most directly, compared to the poles where sunlight reaches our planet at a low angle. In the same way that a hot air balloon rises or hot steam rises over a pot of boiling water, the same thing happens along the equator. Direct sunlight warms up the air, and that hot, moist, low-pressure air rises up into the atmosphere. As the warm air gets higher, it begins to cool off and condense into clouds. This is why we see an abundance of tropical rainforests close to the equator. more warm air continues to rise, pushing the cooler air away from the equator and out towards the north and south, where it will eventually sink back down to the surface. Then that cool air will move from higher pressure along the surface of the Earth back to lower pressure near the equator to start the cycle all over again, completing what we call the Hadley cell rotation. But how does this worldwide circulation of air driven by the sun relate to El Nino and La Nina events? The surface winds created by these Hadley cells are deflected towards the equator due to the Earth's rotation, a phenomenon we call the Coriolis effect. It's this effect that creates the trade winds on either side of the equator, and it's changes to these trade winds that indicate when we will experience El Nino and La Nina events. Historically, the trade winds have been so reliable that sailors have used them to navigate the globe for centuries, hence the name trade winds. Chemical signatures of the ENSO stretch back tens of thousands of years in paleoclimate indicators like coral fossils, and we have written records of the ENSO as far back as the 1500s. El Nino events may have aided Spain in their conquest of the Incan Empire in the 1500s, and in the late 1700s likely contributed to crop failures and unrest that sparked the French Revolution. Despite this long record of ENSO activity and the massive impact it has on worldwide weather and environments, it wasn't until the 20th century that we finally started to understand the mechanisms behind it. The first defining breakthrough came in the 1920s, when a British scientist named Sir Gilbert Thomas Walker set out to better understand the strength of monsoons in India. In his search for a way to predict monsoon strength, he ended up documenting the Southern Oscillation, a repeating shift in air pressure that happens across the equatorial Pacific Ocean. This oscillation was part of another large-scale air circulation that had not been documented before and was later named the Walker Circulation. Remember how I said that Hadley cells circulate air north and south? The Walker Circulation is just like Hadley cells, except instead of moving air north and south, the Walker Circulation moves air to the east and west over the equatorial Pacific, and instead of being driven by sunlight, the Walker Circulation is guided by the easterly trade winds and ocean temperature. It would be 60 more years before scientists were able to connect these changes in air pressure over the Pacific with the alternating pattern of warm and cool surface water in the Pacific. Combined, these make up what we now know as the El Nino Southern Oscillation, ENSO. El Nino refers to the changes in sea surface temperature, and the Southern Oscillation refers to the simultaneous changes in air pressure. Unlike Hadley cells that reliably move air north and south, the equatorial Walker Circulation is not consistent and can experience colossal shifts as part of the Southern Oscillation. Every few years, the surface temperature and trade winds over the Pacific experience fluctuations, signaling an oncoming shift in the Walker Circulation. In turn, these shifts, which we refer to as El Nino or La Nina events, can upset the balance of weather and ecosystems over the entire Earth. So, what happens to the Earth during each of these? During neutral ENSO periods, the sea surface temperature and trade winds are near average conditions. Trade winds blow across the Pacific Ocean, guiding warm surface waters to travel west from South America towards Australia and Asia. As that warm surface water moves west, it makes way for deep, cooler waters to rise up in its place. This ocean circulation brings nutrient-rich cool water to the surface in a process called upwelling, where it feeds phytoplankton and in turn supports other parts of the ecosystem like fish. In neutral periods, weather across the world occurs more or less as expected. This can include normal hurricane development in the Atlantic and average monsoon rainfall across Southeast Asia. Walker circulation drives columns of warm, moist air to rise up above Southern Asia and Northern South America and Middle Africa. So it's no coincidence that these three regions are where we see a concentration of vast, lush rainforests. The influence of this equatorial airflow is vast, so it's easy to imagine how changes to this system could cause a ripple effect around the world. The first signs of trouble are when the trade winds begin to weaken and sea surface temperatures rise in the Pacific, which can indicate an oncoming El Nino event like the one we experienced in 2023 and 2024. During El Nino, the colossal columns of warm air that rise above our world's rainforests are shifted to the east or west. This change disrupts Asia's monsoon season with prolonged droughts and water scarcity, and affects the livelihoods of billions of people in East Asia. The last El Nino also brought 9 atmospheric rivers to the western United States that led to major transportation issues, dangerous landslides, and flooding. You can think of an atmospheric river like a river of moisture streaming through the air. When these atmospheric rivers reach land, they release all that moisture, causing monumental precipitation. Everywhere on Earth, this shift in water circulation is felt during El Nino. However, the changes you experience in your local weather conditions may be completely different from the changes another person sees in their local weather elsewhere on our planet. El Nino typically brings a reversal of the normal conditions for a given area. This is why places like East Asia or the Amazon rainforest, which typically get plenty of rain, will experience drought during an El Nino event, or why usually dry climates like Western North America will experience tremendous rainfall events. The recent El Nino event was also responsible for worldwide shipping delays in 2023, as there wasn't enough water to feed the Panama Canal, which relies on consistent rainfall to accommodate all of the cargo ships hoping to pass through. El Nino is described as the warm part of the ENSO cycle because Pacific sea surface temperatures are higher than average during this time. In addition to changing worldwide weather patterns, this also negatively affects ecosystems. Take, for example, coral reefs. They rely on particular sea surface temperatures to survive and support some of the most important and biologically diverse life on Earth. Corals have a symbiotic relationship with algae, but an increase in water temperatures can cause the coral to expel this algae, leaving it drained of color and vulnerable. A reef can recover from this bleaching if conditions improve in time, but their risk of dying is high, and the last El Nino event was no exception. An unprecedented 99.7% of Atlantic tropical reefs were impacted by bleaching level heat stress during the 2023 to 2024 El Nino event, as part of the 4th worldwide mass bleaching event in recorded history. The warmer Pacific waters and weakened trade winds from El Nino also caused the upwelling of cooler, nutrient-rich water to temporarily slow or stop, leading to a dire situation where less phytoplankton means large numbers of fish must migrate or perish. As you can imagine, this ripples across the food chain and can impact other animals. For coastal families and communities who rely on those fish for nourishment or income, this El Nino effect can be devastating. Now that we've discussed what it's like during a neutral ENSO period and the destructive changes that can happen with El Nino conditions like we saw in 2023 and 2024, what can we expect from this upcoming La Nina phenomenon? La Nina is the other extreme. This period is marked by stronger than usual trade winds and cooler than average Pacific sea surface temperatures. Well, while El Nino usually causes the reversal of neutral conditions, the best way to understand La Nina is to think of it as a more intense version of neutral conditions for most parts of the world, with a few exceptions. During La Nina, the neutral columns of rising warm air above South Asia and Eastern North America become more pronounced, while the typical column of warm air above Africa reverses. Just as your experience of El Nino is highly dependent on where you are located, the same is true of La Nina. As of August 2024, the US National Oceanic and Atmospheric Administration predicts a 66% chance that La Nina will develop between September to November of 2024 and a 74% chance that it will last well into the Northern Hemisphere's winter of 2025 to 2026. And as of this video, models are predicting a roughly 50% chance that this La Nina event will peak at a moderate strength. However, while forecasts for a La Nina event happening are usually correct, the predicted strength for these events will likely change from month to month. A strong El Nino ending in 2024 does not necessarily mean the upcoming La Nina will be as extreme. Sometimes a strong El Nino leads to a strong La Nina, but other times a strong El Nino is followed by a weak La Nina. With only 10 times in the historical record where the ENSO has changed between El Nino and La Nina within a 1-year time period, as is expected with this year's switch, there just isn't enough historical data to draw many conclusions. Besides, scientists warn that the strength of an ENSO event does not always line up with the severity of its impacts. So what do we know about the upcoming La Nina? For the northern part of North America, La Nina brings with it a colder, wetter winter, while the southern part of the continent might experience a warmer and more dry winter. And notably, La Nina will increase the likelihood of a more active hurricane season in the Atlantic, with the potential for more and stronger hurricanes. For East Asia and Australia, this typically means a significant increase in rainfall, while in Africa, La Nina can mean some areas to the west are more wet, while Eastern Africa tends to experience more drought. The connection between ENSO and Europe isn't quite as clear, since the continent is further from the source, but La Nina is expected to bring lower than average temperatures to Central and Western Europe, with less precipitation across the mainland this winter, and more precipitation to the north and south. There's one final thing we need to talk about when it comes to La Nina predictions. The El Nino and La Nina extremes of the ENSO have been happening for millennia, but what's less certain is how global warming from climate change will impact this cycle. While we see short-term, localized temperature swings from ENSO, the all-over trend of global warming continues on an upward trajectory. This means we are entering uncharted territory. There's clear evidence that as our planet continues to warm from climate change, the occurrence of severe weather will escalate. But the ENSO is a complicated, worldwide, and in many ways, still an unpredictable phenomenon. Just in recent history, El Nino and La Nina events have become stronger and more frequent, leading to more droughts, floods, heat waves, wildfires, and extreme storms, like we saw during the last La Nina event that lasted for 3 years, from 2020 to 2023. Exactly how global warming may impact the ENSO cycle is unclear, but we do know that climate change is likely to amplify that too. Luckily, life on our planet is nothing if not resilient and adaptable, and as our world continues to change and experience the millennia-old ENSO swings, scientists will learn more each year and be able to improve predictions about the complex climate system. The approach in La Nina will undoubtedly teach us more about our planet's climate. Let's hope we are paying attention and use these lessons to adapt and prepare for our future in sustainable ways. I'd love to hear in the comments what questions you have about our planet's climate. Thanks for watching. Making this video required some long-term planning and work, which we were only able to do thanks to the consistency and sustainability of your memberships as Astronauts on Patreon. A huge thank you to everyone who has signed up. And if you'd like us to make more videos like this, you can join with the link down below. When you join, you'll be able to watch the whole video ad-free, see your name in the credits, and submit questions to our team. Once again, a huge thank you from myself and the whole Astrum team. Meanwhile, click the link to this playlist for more Astrum content. I'll see you next time.